Hello everyone, I'm Huayao Wu from Nanjing University. In this video, I will present our work, Combinatorial Testing of RESTful APIs, which is accepted in this year's ICSE conference. Representation state transfer, or REST, represents a popular architecture style for building APIs of modern web service. In this style, each resource of the service is identified by a URL, and management of these resources are realized by HTTP methods like POST, GET, and DELETE. Here, we refer to the combination of a resource and an HTTP method like POSTBOOK as an operation, and the client can execute the operation by sending an HTTP request with appropriate input parameter values. Currently, the Swagger or OpenAPI specification is the most popular choice for web developers to document RESTful APIs. In such a specification file, the operations that can be performed and the input and output parameters of each operation are explicitly described. The availability of such a common specification then motivates researchers to develop many different black box testing approaches for RESTful APIs, but it remains challenging for the effective design of test cases because RESTful APIs usually have a potentially huge and constrained input space, which should be smartly explored to exercise service behaviors. In particular, the available operations of RESTful APIs can be executed in many different orders, and there often exist dependency relationships between these operations, such as a resource should be created before it can be accessed. Meanwhile, each operation also has a number of input parameters, and these parameters can be concretized using many different values. Likewise, there are also dependency relationships between these parameters, such as some parameters must be set at the same time. In order to address the huge and constrained input space, different approaches have been proposed. For example, in the operation level, approaches like model-based and fuzzing are developed to construct operation sequences to reach and test every testable operation. While in the input parameter level, a variety of strategies are also available. However, these existing approaches do not take the interactions between operations or the interactions between input parameters into account. And at the same time, although the constraints between operations can be appropriately handled, there is no approach that can automatically extract and handle the constraints between input parameters. Hence, in this study, we seek to adopt the concept of combinatorial testing to test RESTful APIs. The core idea of combinatorial testing is to create a test model to depict the input space of the software under test, and then generate a carving array as a test suite to cover and test the combinations between a certain number of parameters. In particular, assume that the behavior of a software is influenced by 4 parameters, P1 to P4, and each parameter can take values from the value domain 0 and 1. We refer to a combination of T parameter values as a T-way combination, and a T-way carving array ensures to cover every valid T-way combination at least once. This table gives a 2-way carving array of the example, and from this table, we can see that all 3 valid 2-way combinations between P1 and P2 appear at least once in the array. In addition, the behavior of the software can also be influenced by different events. In this case, we refer to a permutation of T events as a T-way sequence, and the T-way sequence carving array can then be used to cover every valid T-way sequence at least once. In this example, there are 4 events, O1 to O4, and the 3-way sequence carving array consists of 3 event sequences. For O1, O2, and O3, we can see that all valid permutations of these three events appear at least once in this array. On the basis of the above carving array and sequence carving array, we then develop a systematic and automatic approach, REST-AT, to test RESTful APIs. REST-AT is systematic in that it covers interactions of a certain number of operations and also interactions of particular input parameters in each operation. REST-AT is also automatic in that the complete testing process, including the creation of combinatorial test models, is fully automated. This picture gives the overall workflow of the REST-AT approach. Giving a Swagger specification as input, REST-AT will use a two-phase strategy, including operation sequence generation and input parameter value rendering to generate HTTP requests. The first phase is operation sequence generation. REST-AT seeks to model the input space of operations and generate a sequence carving array to determine the execution orders of operations. In this phase, it's easy to extract the available operations from the specification, and the problem is to handle the constraints between such operations. To this end, REST-AT utilizes the layer relations of resources and CRUD semantics to determine the validity of each single TW sequence. The basic idea is that a resource and its sub-resources cannot be accessed before the resource creation or after the resource deletion. If this condition is satisfied for all operations in a TW sequence, then we say this TW sequence is constraints satisfying. For example, the tree structure gives the layer relations of four resources of a service. The two-way sequence getBookID postBook is invalid because the BookID resource, which is the sub-resource of book, is accessed before the creation of the book resource. Similarly, the two-way sequence deleteBookID getBookID is also invalid because the access of the resource appears after its deletion. Within this constraints hunting strategy, REST-AT then uses a greedy algorithm to generate a TW sequence carving array to cover combinations of any T operations. This algorithm follows a common one sequence at a time process, and at each time, it generates an operation sequence to cover the most previously uncovered TW sequences and repeat until all TW sequences are covered. To generate each single sequence, the algorithm will start from an empty sequence S and then find the set of candidate operations for extending S. Here, an operation is a candidate operation if it is not included in S and at the same time, appending the operation to S does not violate the constraints. Then, the algorithm will evaluate the TW sequence coverages that can be achieved by appending each candidate operation and select the best one for extension. Here, an operation is a candidate operation does not mean that this operation can be directly executed after the existing sequence. For example, the getBookID operation can be used to extend post-author, as this does not violate the constraint. However, the getBookID cannot be directly executed because the book resource is yet to be created. As such, the algorithm will additionally rely on the CRUD semantics to determine the predecessor operations. Finally, the algorithm will append the operation selected and its predecessor operations to the current sequence, and this process will repeat until the sequence cannot be further extended. Once the sequence carving array is obtained, the next phase is input parameter value rendering. Given each single operation sequence, REST-AT will try to execute operations in the sequence one after another and generate several carving arrays to determine the input parameter values of each operation. To this end, we should first determine the parameters, value domains, and constraints to create the test model. Regarding the parameters, currently REST-AT supports parameters of different types, and each primitive typed parameter is extracted as a unique parameter of the test model. Here, note that some input parameters are tagged as required and some others are optional in the specification. Both of these parameters are considered in REST-AT. Regarding the value domains, a series of heuristic strategies are used. The first is a dynamic strategy, which seeks to search responses received in previous operations to find the required parameter values. The second is a specification, which tries to use the enumerate values provided in the specification or the values extracted from the default and example fields of parameters of the same name. The third is a success, which tries to reuse values that appear in previous successful requests to re-execute the operation. And lastly, if no value domain can be determined using the above strategies, the random strategy will be used to generate 3 random values. Well, for the constraints between input parameters, the current Swagger specification just encourages developers to use natural languages to describe constraints in the description field of input parameters. To enable the automatic constraint handling in REST-AT, we utilize natural language processing to implement a pattern-based approach. The core of the approach is a set of predefined patterns, where each pattern describes the structure of a constraint describing sentence. For a given text, REST-AT will first use a pattern-based matching engine to determine whether the sentence describes a constraint or not. And if the answer is yes, the formal representation of the constraint can be extracted according to the rules specified in the pattern. In this study, we rely on an existing catalog of input parameter constraints to create patterns. This catalog includes 7 types of constraints and provides the most frequently used linguist structures for each type. We carefully studied these structures and created 23 patterns accordingly. Okay, now we have parameters, value domains, and constraints for each operation, and the concrete HTTP request can then be generated. REST-AT uses an adaptive strategy, and the aim is to ensure the successful execution of the operation first, and then exercise as many service behaviors as possible. At the first step, REST-AT creates a test model that contains essential input parameters only. These parameters include required parameters and parameters that have dependency relationships on these required parameters. Then, REST-AT uses a popular carving array generation tool, ICSE, to generate a carving array for the test model of essential parameters. Each row of the array exactly indicates an input parameter value assignment, and REST-AT will use this assignment to construct HTTP requests to perform testing. Next, at the second step, REST-AT will extend the test model to include all input parameters to examine more service behaviors. Here, the essential input parameters are combined to an abstract parameter, and the value assignments in previous successful requests are used as the value domain of the new abstract parameter. Similarly, REST-AT will use the ICSE tool again to generate a carving array for all input parameters and construct and send HTTP requests accordingly. At this moment, if all requests fail, REST-AT will repeat the above process and use a different way to determine the input parameter values. It will try to remove some parameters that are hard to assign valid values, and also rely on a different response to determine the value domain. To evaluate the performance of REST-AT, we set up 2 research questions. The first research question concerns the cost-effectiveness of REST-AT when comparing with state-of-the-art approaches, and the second research question concerns the impact of coverage strengths applied in REST-AT. The subject APIs come from two real-world service systems, GitLab and Bing Maps. Since there is no official specification fields for these APIs, we chose to create Swagger specifications based on their latest online API documents. We used an existing Docker image to deploy and test a local version of GitLab and used the publicly hosted service of Bing Maps to perform testing. Regarding the first research question, we compare REST-AT with RESTler, a popular fuzzing tool for RESTful APIs. We set the coverage strengths of operation sequences and all input parameters to 2, as this is the most common choice in combinatorial testing studies. And we set a relatively higher coverage strength for essential input parameters, because we want to examine more interactions of these parameters. In the experiment, we allocate 1 hour time budget for each subject API and repeat each testing approach 5 times. For the testing results, we follow the common practice of RESTful APIs testing, which uses HTTP style codes as the test oracle. A 2-class code indicates a successful request, a 4-class code indicates an invalid request, and a 5-class code suggests a potential defect. For an operation, if at least one HTTP request is successful or the request triggers a defect, we say that this operation is actually tested. And we refer to a bug as a combination of an operation and a 5-class error code. This table summarizes the test results obtained. We can see that REST-AT can generate and test more operation sequences than RESTler. Eventually, REST-AT can actually test about 60% of operations and about 30% of two-way sequences, while these two proportions are only 3% and 0 for RESTler. During this testing process, REST-AT finds 8 bugs where only one of them can be triggered by RESTler. And for the testing efficiency, REST-AT can generate and send more than 4,000 HTTP requests in 20 minutes. By contrast, RESTler takes about 30 minutes, but only 500 HTTP requests can be exercised. Regarding the second research question, we use a base choice experiment to investigate the impact of each of the 3 coverage strengths involved in REST-AT. The base configuration is the one used in the first research question, and we consider a smaller and a higher value for each coverage strength. Here, due to the use of higher coverage strengths, we allocate 5 hours for each API and repeat the approach 3 times. For the evaluation, we calculate the increase rate of different metrics when increasing coverage strengths. For the coverage strength of operation sequence, we can see that two-way coverage tends to be the best choice, as the use of three-way coverages will lead to much more operation sequences and higher testing cost than the use of two-way coverage, but it will not make substantially more operations be actually tested. While for the coverage strengths of essential input parameters and all input parameters, the different choices will not make a great differences in the number of operations tested, as only a low increase rate can be observed. Okay, summing up, in this study, we focus on the huge and constrained input space of RESTful APIs, and we propose REST-AT, a systematic and automatic approach that adopts combinatorial testing to test RESTful APIs. REST-AT uses a sequence carving array to determine the execution orders of operations and uses an adaptive strategy and several carving arrays to determine the value assignments of each operation's input parameters. Finally, the experiments on real-world RESTful APIs demonstrate the cost-effectiveness of the REST-AT approach. Okay, and that's all for this talk, and thanks very much for your time.